Hello, yo, welcome back. All right, so we're going to continue from where we stop. Here, we're going to be looking at area expansion. Okay, so we've already talked about linear expansion, and we're going to look at area expansion. All right, so of course, area expansion is also measured, okay, by the coefficient of area expansivity, which has the symbol beta, right? Coefficient of area expansivity, and please pardon me, the coefficient of area expansivity is given by the symbol beta, okay, and of course is defined as the change in area per unit rise in temperature. Okay, the change or the rise in area per unit rise in temperature, and of course the rising area is given as final area A2 minus A1 divided by A1, then theta 2 minus theta 1. All right, so this is the coefficient of area expansivity beta. Okay, and of course you know very well that the SI unit is still the same SI unit with linear expansivity. So SI unit of area expansivity is still gonna be per Kelvin. All right, so all the type of expansivity will always have per Kelvin as their SI unit. So let's look at a situation where you are being asked to find the area expansivity, the expansion in area, okay, when a substance increases from the original area of 20 centimeters square to final area of 30 centimeters square. Okay, when the rise in temperature, actually the temperature changes from 10 degrees Celsius to to 30 degrees Celsius. Theta 1 is 10 degrees Celsius, and of course theta 2 theta 2 is 30 degrees Celsius, right? So let's look at how we evaluate this. So in this case, apply the formula. The coefficient of area expansivity is given by the increase in area, which of course is gonna be 30, the final area minus the initial area, 30 minus 20, divided by the original area, which of course is 20, then times the rise in temperature, that's gonna be 30 minus 10. Okay, so let's do this. This is gonna be equal to 30 minus 20, that gives me 10, then divided by 30 minus 10 here is 20. 20 times 20, that's gonna be 400. So I'm having 1 all over 40. Okay, so of course 1 over 40 should give me, that should be 0.025 if I'm not mistaken per Kelvin. Okay, can confirm that 0.025. Let me confirm that. So 1 divided by 40, 0.025 per Kelvin. So that is the area expansivity of that particular substance. All right, so please take note of that, and we're going to proceed to cubic expansivity, cubic expansion. And of course, you know that cubic expansion is the expansion in volume. Okay, and of course we express it as the coefficient of cubic expansivity, which is given by the symbol gamma. Okay, so now the coefficient of cubic expansivities by the symbol gamma is actually equal to the change in volume per unit volume, then per unit rise in temperature. So which of course you know very well that change in volume or the rise in volume is V1 minus V2 minus V1 divided by the original volume, which of course is V1. Then the temperature rise is theta 2 minus theta 1. All right, so please take note of that. And now there's one thing about volume expansivity. Okay, so now this particular volume expansivity, when you measure it for a solid, okay, if we are looking at a solid, if you measure this for a solid, then you are gonna have an accurate value, okay, for a solid, because when you hit a solid is a rigid body, so a solid don't need to be in a container. But when you measure it for a liquid, there's gonna be, okay, there's gonna be what you're gonna have as the cubic expansivity of liquid is going to be of two type. Okay, now one type of cubic expansivity of liquid is known as the apparent. Okay, it's known as the apparent cubic expansivity, and the other type of cubic expansivity of a liquid is actually the real cubic expansivity. All right, so please take note of that, and I'm gonna uh, illustrate the difference between the two. So we have the apparent cubic expansivity of a liquid, and of course we have the real cubic expansivity. So what's the difference between these two? Now, of course, you know very well that a liquid does not have its own shape. Rather, it takes the shape of the container. So if I want to actually, if I hit a liquid, okay, I'm not going to hit that liquid directly. That liquid would definitely have to be in a container when I apply the heat. Okay, so definitely if I apply the heat to a liquid that is inside the container, it is called that both the container and the liquid itself is receiving the heat, right? So that is to say that it's not only the liquid that will expand, the container also will expand. Okay, so now that will now bring me to the difference between the expansivity apparent cubic expansivity and the real cubic expansivity. The apparent cubic expansivity is the expansivity that is measured without taking note of the expansion of, okay, the vessel that is containing the liquid. So of course, that is apparent. Why? Because you didn't consider the fact that as you're applying the heat, not just the liquid will expand, the vessel that is containing the liquid will also expand. So that is why we call such expansivity apparent. So when you measure the expansivity of a liquid without considering the expansivity of the vessel, you call that apparent cubic expansivity. But the real cubic expansivity is the expansivity of the liquid that is actually measured, okay, taking into consideration the expansion of the container vessel, right? So invariably now I can actually generate a formula for the relationship for the expansivity. So invariably now I can say that real real expansivity of, okay, the real expansivity is actually given as first, okay, the apparent expansivity. That is expansivity that is actually measured without considering the expansion of that of the containing vessel. Okay, so let me call it gamma A. Let me just use symbol. Okay, let me just use an alphabet. So real expansivity gamma R is going to be equal to apparent expansivity, then plus the expansivity of the containing vessel. All right. So I can use let me see C to represent the containing vessel. So if the vessel is actually a glass, that's going to be the expansivity of the glass. Okay, so please take note of that. So if you want to measure real expansivity, you have to actually, okay, add the apparent expansivity plus the expansivity of the containing vessel of that particular liquid. So I hope that's well understood. I think I'm going to illustrate this using an example, right? So I have a particular question here. Okay, the question goes like this. Real cubic expansivity for mercury. Okay, according to the question, the real cubic expansivity for mercury is given as 1.82, 1.82 times 10 times 10 raised to the power of minus 2, minus 4, please pardon me, per Kelvin. All right. Then, and the linear expansivity of glass. The linear expansivity of glass. Linear expansivity of glass. Okay, which of course the glass is actually contain the mercury. Okay, the linear expansivity of glass is given according to the question to be equal to 8.0, 8.0 times 10 raised to the power of minus 6. All right, so now if the temperature of 100 cm of mercury, if the temperature of 100 cm of mercury, that is the mercury, the initial length of the mercury is 100 cm. According to the question, initial length of mercury is 100 cm, okay? Is in a glass vessel is raised from 30. The initial temperature is 30 degrees Celsius. It's raised from 30 degrees Celsius then to 100 degrees Celsius. Theta 2 is 100 degrees Celsius. All right, so the question is calculate the apparent expansivity. So we have to calculate the apparent expansivity, okay? So now, how do we actually calculate that, the apparent expansivity? This is what you're looking for. From the formula, we know very well, if I make the apparent expansivity the subject of the formula, apparent expansivity is going to be equal to the real expansivity, then minus the expansion, the cubic expansivity of the glass, containing glass, the glass container, okay? Let me use G to represent that. Okay, so now the question is not how do we actually get these parameters? First, we have already known that the real expansivity of the mercury has been, the real expansivity of the mercury has been given. We have that right here. But we don't know the expansivity of the glass, the containing glass vessel. Okay, so, and that's exactly what I will have to actually evaluate, the expansivity of the glass vessel. Okay, now how do I evaluate the expansivity of the glass vessel? Now you discover that at the end of the day I may not use all these parameters to solve to get what I'm looking for. Now, because I am being given the linear expansivity of the glass vessel, so I need to transform this linear expansivity of this glass vessel into cubic expansivity. So, and that is there's always a relationship. Okay, the relationship has it that if you want to convert linear expansivity to cubic expansivity, please pardon me, if you want to convert linear expansivity to cubic expansivity, you multiply it by 3, okay? So if you multiply 3 times alpha, you are going to have cubic expansivity. So which simply means that cubic expansivity is always 3 times linear expansivity. So now invariably the cubic expansivity of the glass is going to be equal to 3 times the linear expansivity of the glass. Okay, so from what we have here, this is going to be equal to 3 times the linear expansivity of the glass is actually giving us 8.0, then times 10 raised to the power of minus 6. Okay, so let's work with that. 3 times 8, of course, that's 24. So I'm having 24 times 10 raised to the power of minus 6. So I can now apply that now into this formula. So having known that, now I can now get my apparent expansivity is going to be equal to the real expansivity, which is giving us 1.82 times 10 to the power minus 4, 1.82 1.82 times 10 raised to the power minus 4. That is the real expansivity, then minus the expansivity, the cubic expansivity of the glass containing glass vessel, which of course here we have 24 times 10 raised to the power of minus 6. Okay, so how do we actually subtract this? Now the way to subtract this is basically I'm going to make sure that I will write this in a standard form in such a way that the this power of 10 will be raised to the power of minus 4 so that I can factorize. How do I do that? Okay, so I'm going to have 1.82 times 10 raised to the power minus 4. Then minus, I'm going to move the decimal point 1, 2 times. If I move this decimal point 2 times, I'm going to have 0.24. Okay, then of course by moving the decimal point, okay, please pardon me, not, yeah, by moving the decimal point 2 times backward, then I'm going to add 2 to this power of 10. Okay, I'm going to add 2 to this 6, this minus 6. If I add 2 to minus 6, I'm going to have 10 raised to the power minus 4. Okay, by so doing now, I can now factorize. Since I now have 10 raised to the power minus 4 as a common factor, I open a bracket. I'm going to have 1.82, then of course minus 0.24. Okay, so we can now evaluate that. Now let's get a calculator. So this is going to be equal to 1.82 minus 0.24. That's 1.58. So invariably now the apparent expansivity is going to be 1.58, then times 10 raised to the power of minus 4, then of course per Kelvin. So as simple as that. So please take note of this relationship. Okay, real expansivity of a liquid is equal to the apparent expansivity plus the expansivity of the containing vessel. All right, so please take note of that, and we're still gonna solve more questions, and that will definitely be in the next video. All right, see you in the next video. Thank you very much.